This is a brief tutorial on the pH of salt solutions. So first, let's talk about the relationship between Ka and Kb, because some of these ions end up being weak acids or weak bases, and we'll have to be able to get the Ka or Kb of the ions if necessary. So for a conjugate acid conjugate base pair, Ka times Kb equals Kw, which, if you recall, is 1.0 times 10 to the negative 14th power. Therefore, the larger the Ka, the smaller the Kb, and vice versa. So if we have a stronger acid, the weaker the conjugate base, and vice versa. If we take the negative logarithms, we can say the pKa is equal to the negative log of the Ka, and the pKb is equal to negative log of the Kb. You'll see pKa mentioned, for example, in biochemistry, talking about the pKa of certain biological molecules. Similarly to the pH and the pOH, we could say the pKa plus the pKb is equal to the pKw, which equals 14. So let's look at an example. The value of Ka for formic acid is 1.8 times 10 to the negative 4th power. We'll know the value of the Kb for the formate ion, and the pKa and the pKb. So if Ka times Kb equals Kw, the Kb is equal to Kw divided by Ka, which is 1 times 10 to the negative 14th divided by the Ka, 1.8 times 10 to the negative 4th. So we get a Kb for the formate ion of 5.56 times 10 to the minus 11th power. Then take negative log of the Ka to get the pKa, so negative log of 1.8 times 10 to the negative 4th is 3.74. And then pKa plus pKb equals pKw. So 14 minus 3.74 is 10.26. I could have alternately taken the negative log of the Kb I just calculated, and that would have been the same as well. This is just a table indicating what I was mentioning before about the stronger the acid, the weaker the conjugate base, and vice versa. We can see at the top of the table the acid we have is nitric acid. It's a strong acid, complete ionization. Therefore, the nitrate ion would have negligible basicity. That is, the anions of strong acids are neutral. And then you can see HF, hydrofluoric, acetic, carbonic, the ammonium ion, bicarbonate, and then down to hydroxide. You can see that those acids get progressively weaker because of a decreasing value for Ka down to hydroxide, which is really a base, so it doesn't really have any acidity to speak of. But in the base column, you see nitrate, and then you see fluoride, acetate, bicarbonate, ammonia, carbonate, and peroxide, where you can see the peroxide is a strong base, where the nitrate is negligible basicity. So the conjugate acid of a strong base is not really acidic. That would include things like cations, like sodium, and things like that. Now, so let's talk about pH of salt solutions. The diluted aqueous solutions that contain no free acid or base come in 4 basic types. Salts that are formed from the could be formed from the neutralization of a strong base and a strong acid. Aqueous solutions of those salts are neutral. For example, if we react HCl and sodium hydroxide, the salt I form is sodium chloride. Sodium chloride is a neutral salt because the sodium ion and the chloride ion are both neutral. So those alkali metal cations tend to be neutral and form strong bases. And so they form neutral salts. Anions of strong acids are neutral, as we mentioned before. We got salts of the strong bases and the weak acids. So aqueous solutions of salts formed from the neutralization of a strong base and a weak acid are basic. So if we take acetic acid and react it with sodium hydroxide, I'll form sodium acetate and water. Now sodium acetate's my salt. The sodium ion is still neutral, but that acetate ion, as we saw from the table, did have a Kb and is weakly basic. So I've got a neutral ion and a basic ion. So a solution of sodium acetate is basic. You can calculate how basic that is if you have the concentration and whatnot, which we'll get to in a few minutes. We can also have salts of weak bases and strong acids. Aqueous solutions of those salts formed from the neutralization of a weak base and a strong acid is acidic. We got HCl plus ammonia forming ammonium chloride. Now, ammonium ion is acidic because it's the conjugate acid for the ammonia. Chloride ion is neutral, so our salt is acidic. We got weak bases and weak acids. That gets a little bit more problematic. The aqueous solutions of the salts formed from the neutralization of a weak base and a weak acid could be neutral, could be basic, could be acidic. It depends on the values of the Ka's and Kb's. If the Ka and Kb are equal, it's neutral. If Ka is bigger than Kb, it's acidic. If Kb is bigger than Ka, it's basic. Now if we got acetic acid and ammonia, we get ammonium acetate and water. So that could kind of go either way. The ammonium ion is acidic, the acetate ion is basic. It would depend on what the Ka and the Kb are. Ammonium acetate is neutral because the Kb for the acetate ion is 5.6 times 10 to the negative 10th, and the Ka for the ammonium ion is 5.56 times 10 to the negative 10th. Since they're the same, that's a neutral salt. But that will vary salt to salt. So let's determine whether these salts are acidic, basic, or neutral. We're not calculating anything, we're just determining acidic, basic, or neutral. Potassium nitrate. Potassium comes from potassium hydroxide, which is a strong base. Nitrate ion comes from nitric acid, a strong acid, so we have that strong acid, strong base salt, so that would be neutral. Iron nitrate. Nitrate again is neutral. Iron turns out to be acidic. Many of these transition metal ions are acidic, particularly the highly charged ones. That is a Lewis acid, as I mentioned in my other acid-base equilibria presentation. And you could look back at that. In this case, the base it would come from be ferric hydroxide. That's a sparingly soluble base. It doesn't completely ionize, so you could consider it a weak base of sorts, making iron acidic. So that salt would be acidic. Sodium phenolate. Sodium's neutral. Phenol can act as a weak acid, so the phenolate anion would be basic, and so we get a basic salt. Ammonium formate. Ammonium is acidic. Formate is from formic acid, which is a weak acid, so that's a weak base. So again, it's going to depend on Ka and Kb. So Kb for the formate is 5.56 times 10 to the negative 11th for the formate, and the Ka is 5.56 times 10 to the negative 10 for the ammonium. So the ammonium is a bit stronger than the formate, so that salt would end up being somewhat acidic. Now let's actually put some numbers to it. Let's calculate the pH of a 0.1 molar solution of sodium hypochlorite. They gave you the Ka for hypochlorous acid being 3.5 times 10 to the negative 8th. And you can pull that out, again, out of a table of values of Ka's for various acids. Now we know sodium ion is neutral, so we don't really care about that for our intents and purposes. We want to work with the hypochlorite ion, and we know that that's a weak base since it's derived from a weak acid. So hypochlorite plus the water is going to be in equilibrium with hypochlorous acid and hydroxide. We've got a nice equilibrium there that produces hydroxide ion. Ka, we said for hypochlorous acid, was 3.5 times 10 to the negative 8th. So we want the Kb for the anion, because that's what we really are shooting for. Kw divided by Ka, 1 times 10 to the negative 14th divided by 3.5 times 10 to the negative 8th is 2.9 times 10 to the negative 7th for the Kb for the hypochlorite ion. Now we can work it like any other acid-base equilibrium. If you're a little fuzzy on that, look back at my acid-base equilibria tutorial. But we'll work through it. The Kb is going to be equal to the hypochlorous acid times the hydroxide ion concentrations divided by the unreacted hypochlorite ion concentration. So if we say X amount ionizes, we can say X squared divided by 0.1 minus X is equal to 2.9 times 10 to the negative 7th. That Kb is small, so we can make the same approximation we made in the acid-base equilibrium presentation. If it's small, we're just going to assume that X's in addition and subtraction are equal to 0, so we can say X squared divided by 0.1 is equal to 2.9 times 10 to the negative 7th. So all we really want to know is how much ionized, so we can get at the hydroxide ion concentration. So we work through the math. X squared is 2.9 times 10 to the negative 7th times 0.1, which is 2.9 times 10 to the negative 8th. Square rooting. We find the hydroxide ion, which is what we're interested in, is equal to X, which is equal to 1.7 times 10 to the negative 4th. Certainly the other ion would be as well. And we're assuming that the hypochlorite ion is remaining basically unchanged at 0.1. But that doesn't give me pH. The pOH is negative log of 1.7 times 10 to the negative 4, or 3.8. Subtracting from 14, we find the pH of that solution is 10.2, which is about what we'd expect for a basic salt of this concentration. Keep in mind, sodium hypochlorite is the active ingredient in a lot of your chlorine bleaches. This has been a tutorial of pH of salt solutions.